Okay, so hi everyone, my name is Martin Costa, and today I'm going to be presenting our recent SOTA 2024 paper, Nibbling at Long Cycles, Dynamic and Static Edge Coloring in Optimal Time. So this is joint work with Shai Bhattacharya from the University of Warwick and Nadav Pansky and Shai Solomon from Tel Aviv University. Okay. So to start off, what exactly is the edge coloring problem? So as input to the problem, we're just given some simple undirected graph G. And the objective here is to basically compute a function of these edges, which we call a coloring, that assigns values or colors to every single edge such that no two edges that share an endpoint receive the same color, right? So you can think of this as being given a graph and being asked to color these edges so that no two adjacent edges receive the same color, all right? Now we can assume without loss of generality that the range of this function is just integers from 1 to some integer k. And we can notice that the amount of colors required is always going to be at least the maximum degree of the graph. And this is just because take some node of max degree and all of the edges incident upon this node are all going to have to receive different colors, right? So we always require at least delta colors for any coloring of a graph that we produce. And really the question is how small can we make k, right? Because we can always just assign a different color to every single edge and just compute one of these things trivially, but it's more interesting when we try and use as few colors as possible. And it was actually shown by Vizing that any graph can be colored with delta plus 1 colors. Once again, where delta is the max degree of the graph. So we always need at least delta, and we can do it with at most delta plus 1, even though it's not necessarily particularly efficient to compute a delta plus 1 coloring. And actually, in general, it's NP hard to determine whether or not delta is sufficient or not. So delta 1 is really the best we can hope for. So in this talk, we're really going to be concerned with the dynamic setting. So in the dynamic setting, as input, we're given a sequence of updates, each update being an insertion or deletion of an edge from some underlying graph, which is evolving over time. And we also assume that we're given some parameter delta, which is an upper bound on the maximum degree of the graph at any point throughout the entire sequence of updates. So we're given this parameter delta, and we're just guaranteed that the maximum degree of the graph never exceeds this value of delta, okay? So our goal here is really to maintain some coloring of the graph as it evolves over time, and let g of t denote the state of the graph t after the teeth update, after the teeth insertion or deletion into the graph. Then what we want to do is after the teeth update, after the teeth edge is either inserted or deleted, we just want to update the edge coloring that we're maintaining of the graph to be an edge coloring of the brand new graph. That's just changed via an edge insertion or deletion. And we really care about two metrics here. The first one is the update time, so the time that it takes to actually perform this update. And we also care a little bit about the recourse. So the recourse is the number of changes that we make to the actual coloring in order to modify it to be a coloring of the brand new graph after an update. And the reason that we care about recourse is that as long as we're maintaining these objects and explicitly maintaining the coloring, then the recourse will always be a lower bound on the number of on the update time, just because we actually need to go through and manually change every single one of these colors, right? So what results do we actually obtain in the setting? So to start off, we ask the following key questions. So the first one is whether or not for some constant epsilon, it's possible to maintain a 1 plus epsilon delta coloring in constant update time, right? So we want to maintain kind of like a 1 plus epsilon approximation. So we have 1 plus epsilon delta colors, and we just want to maintain an edge coloring that uses at most this many colors, and every single time an edge is inserted and deleted, we want to spend only constant time updating this. Now, the first thing to note is that a dynamic algorithm that has constant update time also implies a static algorithm that runs in linear time. This is basically because we can just feed all of the updates one by one into the algorithm, and the algorithm will spend constant time per update handling these updates. And in linear time, it will just construct a solution to the entire input. So this leads to the following strictly easier question, which is for some constant epsilon, can we just produce a 1 plus epsilon delta coloring in linear time, right? So if we tackle this easier question, which we really need to be able to answer in order to be able to even try and tackle question 1, which is much harder. So the simplest thing that's known for this is if we are okay with having a 2 plus epsilon delta coloring, where epsilon is some small but absolute constant, then the following trivial algorithm is sufficient, where we basically scan through the edges in some arbitrary order, and then while looking at some edge E, we just sample uniform random colors from some pool of 2 plus epsilon delta colors until we find some color which is not currently being occupied by the edges adjacent to this current edge, okay? And as long as epsilon is greater than 0, it's not too difficult to show that this thing can be implemented to run in linear time with high probability. But this only works when epsilon is greater than 0. If we care about even just getting a 2 delta coloring, which corresponds to the trivial greedy algorithm, where basically we just once again scan through the edges in a completely arbitrary order, and every time we look at an edge, we just pick one of the colors that's not currently occupied by its neighbors. And as long as there's 2 delta minus 1 many such colors, this is always possible. It's not even known how to give a linear time implementation of this algorithm. We can give a near linear time implementation. We can do this in n log delta time by just doing like a binary search, but it's not known how to reduce this to linear time. So even in this simpler, even for the simpler question, the static setting, it's still not known how to get a linear time algorithm, okay? So we were actually able to answer both of these questions in the affirmative, and we were able to produce the following 2 results. So in the static setting, we get a 1 plus epsilon delta coloring in linear time, where epsilon is just some absolute constant, as long as delta is some sufficiently large polylog term, where the precise exponent in the polylog will indeed depend on this constant epsilon. And we can essentially get a dynamization of this result where we can maintain such coloring in constant update time, once again, where the maximum degree of the graph is some sufficiently large, like polylog quantity. And the reason for this lower bound is essentially that we need enough concentration for the probabilistic analysis to go through. Okay, so what are the previous results in this area? So what is known? If we care about getting a dynamic algorithm with the best possible update time, Duan et al. Gave the first algorithm that's able to maintain a 1 plus epsilon delta coloring in polylog update time, where delta is some sufficiently large polylog term. And this was subsequently improved by Christiansen, where the update time is a bit larger, but it's still polylog, and it doesn't have any restriction on what the value of delta can be. Delta can just be anything here. And if we care about minimizing the recourse, so the number of changes that occur in the graph, that occur in the coloring after an update, there's a result by Bhattacharya et al., which shows how to get poly 1 over epsilon recourse, which doesn't have any dependence on NR delta. And once again, here we require delta to be some sufficiently large polylog as well. However, this algorithm of Bhattacharya et al. Is not known to be implementable efficiently. So this is purely for the recourse, okay? So now armed with these 3 results, if we try and kind of tackle this problem of trying to get constant update time in the dynamic setting, we run into some barriers. So the first barrier that we run into is basically this soft lower bound. So there was a result by Chan et al. From SOTA 2018, which basically says that essentially there exists some graph where you can basically construct a 1 plus epsilon delta edge coloring of this graph for any sufficiently small epsilon, where if you insert or delete the appropriate edge from this graph, in order to be able to update this coloring to be a coloring of the new graph, you're going to have to modify the colors of at least log n edges, where everywhere here we're just treating epsilon as some constant. And this is a bit of an issue because it means that any algorithm that is analyzed by assuming that the input is just that you have like some completely arbitrary coloring in the graph at some point, and you want to extend this to to a brand new coloring after you take some arbitrary edge and insert it or delete it, any analysis that works like this is going to have a lower bound of log n. You're not going to be able to beat this. And in particular, the results of Duan et al. And Christiansen use this technique. They're analyzed in this manner by extending arbitrary colorings. And this isn't going to be sufficient for these purposes. You're going to have to take a different approach, okay? So what can we do? Well, the algorithm of Bhattacharya et al. Doesn't do this. It basically maintains a coloring from some nice distribution. And because they do this and the coloring is coming from some distribution and isn't assumed to be completely arbitrary at every point from an analytic perspective, their techniques are not subject to this lower bound. So they can bypass this lower bound. However, there's still a bit of an issue and we run into a different problem here. And this is because their algorithm is based off of a static algorithm, which is commonly referred to as the Nibble algorithm. And this algorithm basically only works on near regular graphs. So you need to assume that all of the nodes in the graph have degree very close to delta in order for this algorithm to work. And this is a bit of an issue because in general, we don't want to assume that our algorithm only works on regular graphs. We want it to work on arbitrary graphs. But in order to make the analysis go through, we need to use some regularization gadgets where we take some arbitrary graph and we add some edges in order to make the graph near regular. And this basically leads to some significant overhead in the static setting, and in the dynamic setting, this manifests as some significant preprocessing time. So we still don't get the result that we want. And the question is, can we somehow bypass the need for these gadgets? And our main conceptual contribution is that we basically apply the subsampling technique of Kulkarni et al. From stock 22 in order to bypass the need for these regularization gadgets. And I'll describe what all of this means in more detail in a moment. And essentially, we end up coming up with a brand new variant of the Nibble algorithm, which works on arbitrary graphs and not just near regular graphs. And because we don't have any need for regularization gadgets, we can implement this thing efficiently with the appropriate supporting data structures, and we get our result. So I'm now just going to spend a bit of time describing our static algorithm and how this works, and then at the end briefly describe how we can turn this into a dynamic algorithm. So to start off, how does the Nibble algorithm actually work? So suppose we're given this graph as input and we want to run the Nibble algorithm on this graph. How do we do this? So we begin by just having all of the edges uncolored. And this algorithm will run for t rounds, where t is some poly 1 over epsilon. And it will have some pool of 1 plus epsilon delta colors, which it uses to color this graph. So for every single round, what the algorithm does is it first samples each edge that's currently uncolored with probability epsilon independently. And then it takes every single one of these independently sampled edges, which it's now going to try and color, and it samples a color from this edge uniformly at random from its palette. Its palette is just defined to be as the colors that are available to this edge, so not currently occupied by one of its neighbors at the start of this round, okay? So it samples one of these colors uniformly at random and independently for all of the edges that have just been sampled. And then what it does is it declares edges that have conflicts to fail. So if two edges that are incident upon each other, like share a neighbor, receive the same color during this round, then we declare these edges as failed, and then we just repeat this process. Okay, so we don't uncolor these edges or anything. We just leave the colors as they are, but we just note down somewhere that these edges have failed, and we'll have to deal with them later. And we just repeat this process. We sample some more uncolored edges. We sample colors from their palette. Note that any edge will never be able to receive a color that's already been assigned to one of its neighbors in a previous round, but it might be assigned a color that's being assigned to one of its edges receiving a color in the same round. Okay, so when it fails, edges fail because of other edges in the same round receiving the same color. And we repeat this process for t rounds. And then what we do is we just take all of the edges who have either failed or never been sampled to be colored, and we just run a greedy algorithm on these edges. And the idea is that the graph consisting of such edges is going to have a small maximum degree. Okay, and this is it. This is just how the algorithm works. And how does the analysis of this algorithm work? Well, it's fairly complicated and involved, but one of the things that's kind of crucial in this analysis is that we basically want to be able to argue that the palettes of the edges of of all of the edges in the graph, particularly at the point where you're actually sampling a color from this palette, we want to argue that these palettes are sufficiently large. And this is for two reasons. One, from an analytic perspective, it's crucial to ensure that it's non-empty so that such colors will actually exist. And secondly, it's that as long as the palettes are sufficiently large, you can actually implement this process efficiently, okay? And in particular, as long as it's the palette of an edge is at least delta times some poly epsilon, you can basically sample a color from this palette in poly 1 over epsilon time, and this will lead to a linear time implementation whenever epsilon is some constant, okay? Now, the issue is that near regularity is crucial in order for the concentration bounds in this analysis to actually go through. And the question is, can we somehow perform a different analysis, right? Is there a way that we can analyze this algorithm without needing this near regularity? And it turns out that at least showing the fact that the sizes of these palettes are sufficiently large is quite easy as long as we assume that the input is a forest. Okay, so if the input to the graph is a forest, then the algorithm is much easier to analyze. And this is basically because things that are usually not independent are independent when the graph is a forest, right? So let E be some edge that's sampled during round I, and consider the state of the algorithm after the first I minus 1 iterations. So it might just look something like this. And now consider the graph consisting of the edges that appear in the first I minus 1 rounds. So these are the edges that have received their colors here. And the dashed edges are the edges that appear in rounds I or later, so haven't been colored yet. And notice that the two endpoints of E will appear in different connected components. This is just because the graph is a forest, right? And if you can denote the palette of U and V, so the colors are available to the nodes U and V by PI of U and PI of V respectively. And these palettes will basically be independent of each other. If I tell you that some color is not available for the edge U, this gives you absolutely no information about the colors that are available to V, because U and V aren't connected in the graph at this period of time. And because of the local structure of the algorithm, basically these palettes will just be independent of each other. And this basically allows us to get sharp bounds on the palette, on the size of the palette of the edge E, which is just the intersection of the palettes of U and V. And we're able to lower bound this by some delta poly epsilon. And this basically allows us to give a linear time implementation of this algorithm. And of course, there are various other things that we need to analyze too, but this is one of the main components, and hopefully this does a good job at illustrating why it's much simpler in this case. Okay. So this is, a good starting point, but forests are very restricted classes of graphs. It's unlikely that we're going to be able to reduce the problem of edge coloring to just edge coloring forests. But are there more general classes of graphs that can be analyzed in this simple manner or using these ideas? Well, it turns out that we have something a little bit stronger here, which is basically that if you have some edge within the graph, the only thing that matters from the perspective of this edge is just the t+1 neighborhood of an edge E. So in particular, the color that's assigned to this edge by the algorithm will only depend on the t+1 neighborhood of the edge. And you can prove this claim pretty easily inductively. In particular, the color assigned to an edge E by the algorithm only depends on the I+1 neighborhood of the edge, where I is the round during which it's colored. And then by induction, you can just deduce this more less general result. So as long as the t+1 neighborhood of every edge in the tree, if every edge in the graph is a tree, the same analysis will go through. So we don't need the entire graph to be a forest. We just need the t+1 neighborhood of every edge to be a tree, which is also a forest, of course, but the neighborhood of an edge will be a connected component. And this class of graphs, which we'll refer to as locally tree-like graphs, is much more general than just forests. And suddenly there is hope that we might be able to reduce to this class of graphs. And in particular, there is a reduction by Kulkarni et al. From stock 22, which basically shows that it is indeed possible to reduce to such graphs. So how does this reduction work? So it uses a subsampling technique, which is very simple. The idea is that we have some graph G, and we basically just take all of the edges in this graph G, and we just kind of put them in like eta different buckets, uniformly at random and independently. And this just defines some eta different graphs. Here, eta is just some parameter which depends on delta and epsilon. So we have our graph G, and then we just construct eta different graphs, each of which has the same node set. And then for every single edge in G, we just assign it to one of these graphs independently and uniformly at random. And the main point here is that if we have some cycle in G, it's unlikely to appear in any of the graphs GI. So here, if you so here we take some red cycle that we've just drawn, and the idea is that it's very unlikely that every single one of these edges is going to then be placed within the same graph. So these graphs end up basically being locally tree-like as long as eta is sufficiently large. This isn't quite true. I'm omitting some significant technical details here, but morally this is kind of true. So the idea is basically then that, okay, we have our graph G, we can subsample it into these graphs GI. Well, then why can't we then just run the Nibble algorithm independently on each of these graphs and then just combine the colorings that we have at the end? So more precisely, our algorithm is the following. So we start off with our graph G, we subsample it into these GI. We then run the Nibble algorithm independently on each of these graphs using a completely disjoint set of colors for each of these graphs. So we don't do this greedy coloring part at the end. We just do the rounds where we produce these tentative colorings. And then we take all of these graphs. We basically take the union of these graphs and their colorings. And then we take all of the edges that failed across any of these independent Nibble algorithms that we're running on all of these GI and all of the edges that were never sampled to be colored. And we just take the union of all of these and we just run a greedy algorithm on all of these things together. And this is how our algorithm works, okay? And as long as delta is sufficiently large in order to ensure that all of the concentration bounds are able to go through, this will produce a 1 plus epsilon delta coloring, and it can be implemented efficiently to run in linear time. Okay, so this is how our static algorithm works. So how can we dynamize this algorithm? So the idea is that we basically just have a dynamic algorithm that explicitly maintains the output of the static algorithm at every point in time. Okay, so we can fix all of the random bits used by the algorithm, by the static algorithm in advance. So all of the random bits used for the subsampling and for the sampling of colors during the run of these Nibble algorithms on the subsampled graphs and so on. And this basically means that it completely fixes what the output of the algorithm should be at any point in time, and it's completely determined by simply the edges that are present in the graph. And after an edge is either inserted or deleted, we can then basically just iterate through these rounds and propagate the changes in the coloring in order to basically see which edges are supposed to be changing colors. And informally, the idea is basically that we can maintain some appropriate information that allows this process to be done efficiently. So when an edge changes color, we can basically maintain the information telling us which other edges should be changing color because of this edge changing color. And this basically allows us to implement the algorithm so that the update time is proportional to the recourse. And we can analyze the recourse and show that it's going to be poly 1 over epsilon by a similar argument to Bhattacharya et al. From SOTA 21. And then this in turn gives us poly 1 over epsilon update time. Okay, so thank you very much for watching. And if you're interested in seeing more of the details, then feel free to have a look at our full paper. It's available on arXiv. Thanks.